So what we are going to do today is first give a formal definition of the eigenvector and the eigenvalue, and then we're going to walk through the procedure how we calculate the eigenvalue and the eigenvector. In the end, we're going to give some examples of symmetric matrix and defective matrix. Let me start from the geometric interpretation. In this geometrical interpretation, think about this matrix A as the transformation matrix. When you have a transform matrix, when you multiply to any vector, the return result is the image of this vector after the transformation. For example, a projection matrix times a vector, you get the shadow or the projection image of this vector. And the equation A times V equals lambda times V basically telling you the image is parallel to the vector V itself. In other words, the image stays on the same straight line with your original vector V. Well, it depends on the lambda is positive or negative. It's smaller than 1 or bigger than 1. And the only change is the magnitude. When the lambda is bigger than 1, the magnitude of the image will longer than V. When the lambda is less than 1, the magnitude of the image is shorter than V. And the third case, if the lambda is negative, the image will go to the opposite direction of this original vector. So, but still stay in the same straight line. So what is the geometric meaning of this eigenvector? It is the vector under the transformation does not change direction or go to the other direction 180-degree opposite. In this example, we look at the mirror reflection matrix. The original vector, this one, let me call it V. The transformation simply reflected to the opposite side of this vertical line. And then you get the mirror image on the other hand. This is the A times V. Now let's check. If you have a vector x1, x2, multiply the A, what you get? You multiply negative 1 times x is negative x1, 0 times x2 is still 0, 0 times x1 is 0, 1 times x2 is x2. Then you see you just need to switch the sign of this x coordinate. See, look at this way. So if here is 2, then this is negative 2. If this is 1, then you got back to negative 1. Now this point is the mirror reflection, so negative 1. That's the only change. So we are looking for the vector. If you take the transformation, the image stay either the same direction or exactly the opposite direction. So what are those vectors? Well, you can find the 2 of them. Let me start from this easy one. What you're going to do with this vector? if the coordinate is 0, 1. Well, you change the 0 to negative 0, it's still 0, 1. Of course, the mirror image on the mirror is the same image. It does not change. So that's one of the eigenvector. And what's the eigenvalue? Well, the eigenvalue is going to be 1. Look, if we multiply this matrix to 0, 1, like this one, you still get a 0, 1. Now, negative 1 times 0 is 0, and the 0 times 0 is 0, 0 times 0 is 0, 1 times 1 is 1. Does not change. So the eigenvector is 0, 1. The eigenvalue for this is 1, because this lambda equal 1 here. That's simple enough, right? Let's look at the next one. The next one, change to green color. Look at this one. If you got this vector, which is 1, 0, when you do the transformation, you get into the opposite direction. Still parallel, right? And you just change this into negative 1, 0. Well, if you change to the opposite direction, we know this eigenvalue lambda should be negative. In this case, it's negative 1. You see it from this picture, but let's look from the calculation. I start from 1, 0. I multiply the a. So negative 1 times 1 is negative 1. And 0 times 1 is 0. 1 times 0 is 0. So you get the opposite direction, negative 1, 0. And the negative 1, 0, you can rewrite, put the negative out, 1, 0. Basically, equals negative 1 times itself. This is simply tell you the eigenvalue is negative 1. So how about other vectors? Well, depends. If you have another vector here, you're going to get to here. From the imager, you know it's not going to be on the same straight line. The direction changed. Except the vertical and the horizontal direction, you can try. You won't find any other direction. You can keep the same direction or the opposite direction. They're going to change the angle. So in this example, you visualize, you get 2 directions, vertical or horizontal. It does not change the line. So we call them eigenvectors. Well, next, let's see how we can find those eigenvalues and the eigenvector. I want you to recall some knowledge in the matrix algebra. The first observation deals with the homogeneous equation. We know this equation always have the 0 solution. You can put x vector as 0. 0 times anything is 0. They're good. And the second, in case this B is non-singular, in other words, the B inverse exists, and then you only have 0 solution. Because if you multiply B inverse to B, and then the B inverse times 0 is still 0, then you only get 0 solution. That's what we learned just in last lesson. And the flip side of this statement is, if you want any non-zero solution, or we call it non-trivial solution, you cannot let the B has the inverse. So the B must be singular. If you want to be singular, that means the determinant of B must be 0. That's so simple. So we already said nobody have interest to the zero solutions because it's obvious. That's why we call it trivial solution. The goal is to find the non-trivial solution to the homogeneous equation. Keep that in mind. Now back to the definition of eigenvector and eigenvalue. We wanted the AV equal lambda V. The imager stay in the same direction as the vector V. So we can rewrite it. AV minus lambda V equals 0 vector. Just to change this right hand to the left by subtracting the lambda V. And now I factor out the V. Remember, non-commutative property of the matrix. You can only factor it out from the right hand. You get the A left, and you have lambda left. Wait a moment. If you really understand the matrix operation, that won't make sense. A could be a 3 by 3 matrix. A 3 by 3 matrix, subtract the number 2, does not make any sense. When you factor it out, don't forget you have to put the identical matrix I there. Now, give you an example. 3x minus 2 x. When you factor out 3x minus 1x, you take out the x, what left? 3 minus 1. The 1 need to be there. If you need the 1 there, in this case, for the matrix, you need the I be there. So we got this equation. Looks like the B times V equals 0 if we let the B equal this A minus lambda I. So I'm seeking the solution of this Bx equals 0. I'm not interested in the zero solution. I want to get no zero solution. Well, we call it no trivial solution. So what's the requirement to the B? I have already said determinant must be 0. So B is this. The determinant of the B is that polynomial. In a minute, when I give you an example, you're going to see when you look at this determinant, because it has the parameter lambda inside, it's going to be a polynomial of lambda. And that polynomial has a name. It's called characteristic polynomial of the matrix A. The name simply say this particular polynomial characterize this matrix. Well, if you set it, I said you need it equal 0, right? If you let this polynomial equal 0, you get an equation. The equation, we call it a characteristic equation. And this roots of the characteristic equation, it's exactly what we talked about. The eigenvalue is the root of this determinant.